Hello Bobcats. So today we're going to talk about valence bond theory and hybridization of orbitals. So valence bond theory focuses on atomic orbitals. So valence bond theory focuses on the atomic orbitals that must have overlapped or blended in order to obtain a particular molecular geometry. This is also known as orbital hybridization. And what happens is that these orbitals will blend or hybridize so that the particular bonding that occurs will happen. So let's look at 5 different elements and see how this works. First, let's take beryllium. So we have beryllium, and if I look at the orbital diagram for beryllium for the valence shells, valence electrons, remember this is valence bond theory. So I'm going to look at the valence electrons. So we have 2s and 2p orbitals, and beryllium has 2 electrons. Now, in this case, beryllium cannot bond because there's no single electrons to pair up with. These are already paired. So what it does is it hybridizes. In other words, it takes this s orbital and one of the p orbitals and makes orbitals of equal energy. Remember, the s is slightly lower in energy than the p. So here we have 1, 2, and these two are called sp hybridized orbitals, and then you have the 2p orbitals up here. And what's happening, you can think of it as, is this s orbital is blending with this one single p orbital. So we have an s and a p orbital that blend to make this orbital that looks like this. It's a big lobe and a small lobe, and it's known as an sp orbital. So we have 2 of these sp orbitals now, and now we have an electron in each one, and you can make 2 bonds with that. You also have the 2p orbitals left alone up here. So now we have these 2 orbitals that have blended together. So we say that this is sp hybridized. The next one we can look at is boron. So let's take a look at boron. And boron has the same orbital diagram, 2s, 2p, with 1, 2, 3 electrons in it. Now in this case, boron can only make 1 bond, but it wants to be able to make 3. So it will hybridize this s orbital with 2 of the p orbitals to make 3 sp2 hybridized orbitals, and then leave the single p orbital by itself up here. And then we have 1, 2, 3 electrons. So it just takes this electron and puts it in that orbital. But now they're all of equal energy. And so it's kind of like you're taking an S. So you're taking the S here, and then you're taking 2p orbitals, and I'm just I'm just going to draw them like this. So 2p orbitals, and we're blending them together to make 3 of these sp2 hybridized orbitals of the same energy. So now we have 3, and then you have the p orbital up here by itself. You didn't do a very good job drawing those, but you'll get the idea. And then we have a p orbital by itself up here. And if you want to, you can think of it as just the same old p didn't hybridize by itself. So now we can have 3 bonds with the boron. And then we have carbon. So let's look how carbon hybridizes. So carbon has the same orbital diagram where you have 2s, 2p, and you got 1, 2, 3, 4 electrons in it. In this case, carbon would only be able to make 2 bonds, but carbon has to make 4. So it takes this 1s and all 3 of the p orbitals and hybridizes them or blends them together to make 1, 2, 3, 4 sp3 hybridized orbitals. And you got 1, 2, 3, 4 electrons, and now I can make 4 bonds. So we're taking an s, and then we're taking all 3 of the p's. I know they're in different orientations, but I'm not going to worry about drawing them in different orientations. So then we have 3 p's, and we blend them together to make 4 times this blended orbital, which is called an sp3 orbital. And then there's no p orbitals left over. So again, beryllium will be sp hybridized. You make 2 bonds. This will be sp2 hybridized, and this will be sp3 hybridized, 4 bonds. So you can think of it, it's got 2 bonding areas, so it's got sp. This has 3 bonding domains or areas, sp2 and sp3. Let's look at 2 more. Let's look at phosphorus and sulfur and see how they hybridize. And so the next would be phosphorus. So if I take phosphorus and start out, and now phosphorus, remember, is on the 3rd energy level, so it's got the 3s, the 3p, and it's got 3d orbitals that are available. They're not being used, but they are available, so we have 3d orbitals. Now, p has 5 valence electrons, so it's 1, 2, 3. Now, there are cases where the phosphorus will make 3 bonds, like this, and have a lone pair, but at times it will want to have 5 bonds, and so we need to hybridize orbitals to make them all of the same energy. So it takes the one of the s's, 3 of the p's, and 1 of the d orbitals, and hybridizes it to make one, 2, 3, 4, 1, 2, 3, 4, 5 of the same energy level bonds, which would be sp3 dehybridized, and then you'd have the 1, 2, 3, 4 d orbitals that were left alone. And now we have 1, 2, 3, 4, 5 electrons that can make 5 bonds. So that's an sp3 dehybridization. And then sulfur will have, if you look at sulfur, it's got 3s, and then it's also got the 3p's, and then it's got the 3d's. So that's 3s, 3p, 3d, and it's going to have 1, 2, 3, 4, 5, 6. So now I have 2 electrons that I can move into d orbitals up here. And remember, this hybridization can only happen on the 3rd level. The dehybridization sp3d and sp3d2 can only happen on the 3rd energy level, because these d orbitals aren't available until the third energy level. So it takes the 1s orbital, the 3 p orbitals, and then 2 of the d orbitals, and it hybridizes them to make 6 equal orbitals. So it's 1, 2, 3, 4, 5, 6. And these are all sp3d2 hybridized. And then you have 1, 2, 3 d orbitals still available, or still left alone up here. And then we had 6 electrons, so 1, 2, 3, 4, 5, 6. And now it can make 6 bonds. So that's the idea of valence bond theory and orbital hybridization. And from that, you can probably understand where we get some of those molecular geometries, molecular shapes, and electron geometries from the other lesson. And we'll stop there, and I'll see you again later.